Have you ever wondered how a truly groundbreaking idea comes to be? We often imagine a lone genius, a sudden flash of insight, a single moment that changes everything. But real breakthroughs are usually more subtle, more patient, and far more interesting. The secret pattern behind most breakthroughs is not a single leap. It's a series of connected steps, a process we can call an adaptive innovation sequence. Think of it as a hidden path being built one stone at a time. Adaptive means each change helps something better fit its environment. An organism, a technology, a society. Innovation equals a new idea or a new way of doing things. A sequence is a chain of steps, one after the other. So, an adaptive innovation sequence is a series of small, interconnected changes. Each new step builds on the ones before it. Imagine building a staircase inside a dark tower. You can't just jump to the top floor. You must lay one step, then the next. Each step is modest on its own, but together they reach what was inaccessible. This gradual, cumulative process is the engine behind huge transformations in history, evolution of the human eye invention of the internet. It's a slow, steady march, not a magical jump. Understanding this pattern is powerful. Look at the world through sequences and you see hidden logic. Many complex systems didn't appear fully formed. They grew from countless trials, happy accidents, incremental improvements, stacked over long periods. By studying these chains, we learn how to foster environments that favor positive change. We can spot when a sequence gets stuck on a bad path and learn to nudge it toward a better direction for everyone. This essay will explore this quiet but powerful force. We'll examine core ideas that make sequences work. Small changes add up the importance of surrounding context. We'll show real-world examples from nature, technology, human society. We'll consider things that slow or block progress. And finally, offer clear, practical advice for anyone, a business leader and aspiring creator, who wants to build paths to a better future. It's a journey into how things become, one step at a time. Yeah. To truly grasp the power of adaptive innovation sequences, we need to understand three fundamental ideas that act as their bedrock. The first, and perhaps most important, is the principle of cumulative change. Small, incremental steps add up over time to create massive transformations. A single genetic mutation might seem insignificant, but over millions of years, a series of such mutations can evolve a simple, light-sensitive cell into a complex camera-like eye. A single software update might only fix a minor bug, but thousands of such updates can turn a clunky early program into the sophisticated application you use every day. Each step creates a new platform for the next step to build upon. The second core idea is context dependence. The value of any innovation depends on what already exists around it. A brilliant idea can be useless if it arrives before its time. The smartphone would have been a fantasy in the 1950s because necessary components didn't exist yet. Miniaturized transistors, high-capacity batteries, wireless networks, graphical user interfaces. Each component was the result of its own long innovation sequence. Innovations thrive when they can plug into a supportive ecosystem. The right step is only right in the right place at the right time. The third principle is feedback and path dependence. Once a sequence starts down a road, it can become self-reinforcing. Early choices can shape all future possibilities. Think of the QWERTY keyboard layout. It was designed to prevent mechanical typewriter keys from jamming, not to be the fastest layout. Because many people learned it and many machines used it, it became the standard. Even today, long after mechanical keys are gone, we still follow that path because switching is costly. Feedback loops, positive and negative, lock in these paths and make them hard to escape. Together, these three principles form the invisible architecture of innovation. They explain why progress is often slow and steady rather than sudden and explosive. Every new idea is in conversation with ideas that came before it. The history of how we got here matters for where we can go next. Keep these ideas in mind and we move beyond the myth of the lone genius to a collaborative, historical, interconnected view of breakthroughs. It is more complex, but ultimately more accurate. To make sense of these complex sequences, we can use a few simple but powerful frameworks, almost like blueprints for understanding how change unfolds. The first and most famous is evolution by natural selection. In the biological world, change happens through a slow, steady process. Random variations or mutations occur in an organism's genes. Most of these changes are neutral or harmful, but occasionally one provides a slight advantage for survival or reproduction in a specific environment. That advantageous trait is more likely to be passed on to the next generation. Over immense spans of time, this simple feedback loop of variation and selection can build incredibly complex structures. Like the wings of a bird, intricate chemical factories inside a plant cell. It is the ultimate adaptive sequence. A second useful framework comes from the study of complex systems. This field looks at things that are made of many interconnected parts: a city, an economy, the internet. In these systems, simple rules governing the behavior of individual parts can lead to surprisingly complex and unpredictable patterns for the whole group. Small changes in one area can sometimes trigger massive system-wide shifts, an event often called a tipping point. For example, a new subway line in one part of a city can completely change real estate values, traffic patterns, social dynamics in a distant neighborhood. Complex systems thinking helps us appreciate how the interconnectedness of parts drives innovation forward in non-linear and often surprising ways. Another important blueprint is the concept of diffusion of innovations. This framework explains how an technology practice spreads through a social group over time. It rarely happens all at once. Typically, a few innovators, early adopters, are the first to try something new. If they find it useful, they influence their peers, and the idea begins to spread to a larger group known as the early majority. This creates a cascade effect, and soon the late majority laggards join in. This process often follows a predictable S-shaped curve, starting slow, accelerating rapidly, finally leveling off as the innovation becomes saturated in the population. Understanding diffusion helps us see innovation not just as an invention, but as a social process of adoption and acceptance. Finally, we have the framework of organizational learning. Companies, institutions, entire industries learn from their experiences, both their successes and their failures. This learning is stored in routines, procedures, company culture, shared knowledge of employees. Each project, each product launch, each market response provides feedback that refines the organization's understanding of what works. This accumulated knowledge makes future innovation easier, as the organization doesn't have to reinvent the wheel every time. However, just like with path dependence, this learning can also make a company resistant to radical new ideas that challenge its established way of doing things. This framework highlights the role of memory and experience in shaping the trajectory of change. Right? So yeah. If adaptive sequences are the paths of innovation, what are the engines that power the journey? Several key mechanisms work together to generate and shape these chains of change. The first and most fundamental is variation. Before any progress can be made, there must be a pool of different options to choose from. In nature, this variation comes from random genetic mutations, the shuffling of genes during reproduction. In the world of technology and ideas, it comes from brainstorming, experimentation, tinkering mistakes. The more diverse the initial set of ideas, the higher the probability that one of them will turn out to be a valuable starting point for a new sequence. A culture that encourages curiosity and tolerates failure is a culture rich in variation. Once variation has provided a set of options, the mechanism of selection comes into play. Selection is the filtering process that determines which variations survive and propagate. In the natural world, the filter is the environment itself, predators, climate competition for resources. In the marketplace, the primary filter is customer choice. A product that solves a real problem or fulfills a desire is selected and thrives, while those that don't are abandoned. This process isn't always about being the best in an absolute sense. It's about being the fittest for a particular context at a particular moment. Selection prunes the tree of possibilities, giving direction to the otherwise random process of variation. A third powerful engine is modularity and recombination. Many complex systems are modular, built from smaller, independent, and interchangeable parts. Think of a computer built from a separate motherboard, processor, memory stick, hard drive. Or think of how Lego bricks can be combined in near infinite ways to create new structures. Modularity dramatically accelerates innovation because it allows for recombination, mixing and matching existing parts to create novel solutions without reinventing everything from scratch. Developers of a new smartphone app don't need to invent a touchscreen or a GPS chip. They can recombine existing modules in a new way to create new functionality. This Lego-like quality is a massive shortcut on the path to novelty. Finally, two interconnected mechanisms, coevolution learning, drive sequences forward. Coevolution describes a process where two or more things evolve in response to each other. A classic example is the relationship between flowers and their pollinators. A flower evolves a deeper shape. The pollinating insect may evolve a longer tongue, which then selects for an even deeper flower. In technology, we see this in the relationship between hardware and software. Faster processors enable more demanding software, which creates demand for even faster processors. This reciprocal dance is complemented by learning, where feedback from trial and error refines ideas over time. Each attempt, successful or not, provides information that guides the next step, making the entire process smarter and more directed as it unfolds. Okay, that's it. Section 5. Nature, Tech, and Us Case Studies in Adaptive Sequences. The abstract patterns of adaptive innovation come to life when we look at concrete examples. These stories show long chains of small, connected steps leading to astonishingly complex and powerful outcomes. Let's begin with nature's most famous example, the evolution of the eye. It did not appear overnight. Hundreds of millions of years ago, single-celled organisms with a light-sensitive protein spot. That spot let them distinguish light from dark, a huge advantage. Over generations, the spot became slightly cupped, giving rudimentary direction. The pit deepened into a pinhole camera that could form a crude image. A transparent layer formed over the opening to protect it. That layer thickened into a primitive lens to focus light. Muscles evolved to change lens shape for dynamic focusing. A network of specialized nerve cells, the retina, developed to process information. Each step was a small adaptive improvement with a survival advantage. Each step was possible because of the platform created by the one before it. The vertebrate eye is the end product of a very long, gradual sequence. In technology, the personal computer follows a similar path. Its sequence begins not with a garage, but with mechanical calculators. and looms in the 19th century. Then the invention of electricity, the development of vacuum tubes for radio, their use in massive, room-sized code-breaking machines during World War II, the transistor at Bell Labs in 1947, a tiny solid-state switch. It replaced bulky, unreliable vacuum tubes. That made computers smaller, faster, and cheaper, enabling the integrated circuit, thousands of transistors on a single chip. That platform made personal computers possible. But hardware was only half the story. A parallel sequence of software innovation unfolded. Early programming languages, more user-friendly operating systems. The graphical user interface, icons and a mouse, made computers intuitive. Networking protocols let machines connect, creating the internet and the World Wide Web. Today's smartphone is the convergence of many sequences: computing, telecommunications, battery technology, and display manufacturing. No single person invented it. It emerged from many long adaptive paths. Our societies are shaped by these sequences too. Consider the emergence of modern agriculture. For most of history, humans were hunter-gatherers, moving constantly. The first step was likely accidental, seeds sprouting near a campsite. That led to deliberate planting. Early farmers selected the best seeds, starting crop domestication. More reliable food let people settle permanently. Villages and then cities could form. Dense living spurred social innovations, systems of governance, laws, writing to keep track of grain and trade. The need to water crops led to irrigation systems requiring large-scale cooperation. Each solution created a new platform with new problems and possibilities. The modern city is the current endpoint of this 10,000-year adaptive sequence that began with a single dropped seed. That is the arc of these case studies. While adaptive sequences are a powerful engine for progress, they do not always move forward smoothly or in a positive direction. Several powerful constraints can slow, stall, or even trap the process of innovation, leading to stagnation or undesirable outcomes. One of the most significant of these is a lack of variation. As we've seen, variation is the raw material for selection. If a system becomes too uniform and new ideas are scarce, there are simply no alternative paths to explore. In agriculture, this is seen in the danger of monocultures. Planting vast fields with a single genetically uniform crop can be highly efficient, but if a new disease appears to which that specific variety is vulnerable, the entire food supply can be wiped out. A lack of diversity makes a system brittle and unable to adapt to change. Another major constraint is the problem of path dependence and lock-in, which we touched on earlier. Once a particular technology standard or institution becomes deeply embedded, it can be incredibly difficult to switch to a better alternative, even if one exists. The QWERTY keyboard is a classic example, but we see this everywhere. Cities may be locked into car-dependent infrastructure, making it difficult and expensive to build effective public transit. Companies can become locked into outdated software systems because the cost and disruption of migrating to a new one are seen as too high. This tyranny of the status quo can keep us stuck on suboptimal paths long after the original reasons for choosing them have disappeared. Coordination problems also present a formidable barrier to change. Some of the most valuable innovations require many different people, companies, or even nations to act in concert. For example, transitioning from gasoline-powered cars to electric vehicles requires a coordinated effort. Automakers need to build the cars, energy companies need to build a vast network of charging stations, and governments may need to provide incentives to encourage consumer adoption. If any one piece of this puzzle is missing, the entire transition can fail. Getting all the necessary actors to align their interests and move in the same direction at the same time is one of the hardest challenges in managing large-scale innovation. Finally, a pervasive constraint is the human tendency toward short-term thinking. Truly transformative innovation sequences often require a long period of exploration and investment before they yield significant returns. The early steps on a new path can be risky, expensive, and may not show immediate promise. In a business or political culture that demands quick, measurable results, there is immense pressure to focus on exploiting and refining existing, proven solutions rather than exploring uncertain new territory. This focus on immediate optimization can starve the very processes of experimentation and play that are necessary to discover the breakthrough paths of the future. It's like eating your seed corn. You get a good meal today, but you have nothing to plant for tomorrow. Understanding the dynamics of adaptive sequences is not just an academic exercise. It provides a practical toolkit for anyone who wants to foster positive change. Whether you are a CEO, a city planner, an engineer, or an artist, there are concrete actions you can take to help guide the flow of innovation in a more productive direction. One of the most powerful strategies is to deliberately design systems to be modular. By breaking down complex products or organizations into smaller, self-contained, and interchangeable parts, you create the conditions for rapid recombination. This means encouraging open standards, creating well-documented APIs, and fostering a culture where different teams can easily borrow and build upon each other's work. A modular world is a world ripe for new combinations. Another crucial action is to actively encourage and protect variation. This means creating space for experimentation and tolerating failure. In a company, this could take the form of a 20% time policy, where employees are allowed to work on passion projects or establishing an R&D lab that is shielded from short-term revenue pressures. For a city, it might mean creating zoning laws that allow for mixed-use development or setting up small grants for community-led pilot projects. The goal is to increase the number of shots on goal by allowing many different ideas to be tested on a small scale. Most of these experiments will fail, and that's okay. The few that succeed can become the starting points for major new innovation sequences. Leaders must also learn to consciously manage path dependence. This involves being vigilant for signs of unhealthy lock-in and being willing to invest in creating transitions to better paths. Sometimes this means maintaining a legacy system while simultaneously building its replacement, allowing for a gradual migration. Other times it might require a bold decision to abandon a profitable but outdated product line to free up resources for the future. It also means being careful about the standards and platforms you adopt today, thinking through their long-term implications. Choosing a path is easy. Escaping one is hard. Wise leaders think not just about the next step, but about the path that step commits them to. Finally, there is the critical challenge of balancing exploration and exploitation. Exploitation is the process of refining and improving what you already do well. Exploration is the search for something entirely new. Both are essential. The best approach is to be ambidextrous, to have parts of your organization focused on efficiently running the core business, while other protected parts are free to wander the frontier. This ensures that you are delivering value today while simultaneously discovering the sources of value for tomorrow, creating a sustainable engine for long-term adaptation and growth. To manage and guide adaptive sequences, we first need to be able to see them. Because these patterns unfold over time and involve many interconnected parts, they can be difficult to perceive in the moment. Researchers and practitioners have developed several methods for tracing these journeys, turning the messy reality of history into a map that can offer guidance. Perhaps the most accessible and intuitive method is the use of historical narratives and case studies. By carefully reconstructing the timeline of an invention or a social change, we can identify the timeline itself, the key steps, the enabling technologies, the dead ends, the happy accidents. Telling the story of how the internet came to be, for example, reveals the crucial sequence from government research academic network commercial platform. A more analytical approach involves mapping the networks of components that make up a system. This can be as simple as drawing a diagram that shows how different technologies depend on one another. For instance, a map of the smartphone ecosystem would show the ecosystem overview apps, the operating system, the hardware, the cellular network. By visualizing these dependencies, we can better understand how a change in one part of the system might create new opportunities or challenges for other parts. This network perspective helps us move beyond a simple linear timeline and see the web of co-evolutionary relationships that drive a system forward. It shows us which parts are central, which parts are peripheral. For a more predictive understanding, researchers often turn to computer simulations and agent-based models. In these models, a programmer can create a virtual world populated by agents, people, firms, organisms, that follow a set of simple rules. By running the simulation, they can see what kinds of large-scale patterns emerge from these simple local interactions. For example, a model could test how a new idea spreads through a social network, or how different market strategies lead to technological lock-in. These models are powerful tools for thought, allowing us to experiment with different what-if scenarios and develop a deeper intuition for the often counterintuitive dynamics of complex adaptive systems. Ultimately, all of these methods depend on the availability of good long-term data. To spot a sequence, you need to look at a process over a significant period of time. This could mean analyzing patent records over decades using archaeological evidence to reconstruct ancient trade routes, collecting years of sales data to map the diffusion of a new product. Without this historical perspective, we are likely to misinterpret the nature of change, mistaking a single data point for a trend, attributing a breakthrough to a single moment of genius, instead of recognizing the long, cumulative process that made it possible. Studying sequences requires patience and a deep respect for the story that history has to tell. The study of adaptive innovation sequences is not just about understanding how change happens, it's also about making responsible choices about the kinds of change we want to encourage. The paths of innovation are not morally neutral. They create winners, losers. They open up new possibilities for some while closing them off for others. They have profound consequences for our society and for our planet. A rapid sequence of automation in manufacturing, for example, can lead to increased productivity and cheaper goods, but it can also cause widespread job displacement and economic hardship for entire communities. The sequence behind a convenient new app might erode privacy or concentrate market power in the hands of a few giant corporations. Conversely, a slow or stalled sequence can lock us into unjust or unsustainable systems. The slow pace of our transition away from fossil fuels, despite overwhelming scientific evidence of harm, is a tragic example of lock-in driven by powerful economic and political forces. The failure to innovate, to rapidly build new paths, is itself a profound ethical problem. Therefore, we must assess the consequences of new paths and critically examine the old paths we continue to follow. Inertia is a choice, and it carries moral weight. As we guide innovation, ask, who benefits from this change? Who is being left behind? What are the unintended consequences for our environment, for our communities, for our democratic institutions? These are hard questions but essential. Making ethics central requires building more inclusive and deliberative institutions. Bring diverse voices to the table. Engineers, investors, social scientists, ethicists, community representatives, the public at large to help shape change. Create feedback loops not just for market success, but for social and ethical well-being. Thinking in sequences forces a longer, broader view of responsibility. Small choices today can set in motion self-reinforcing dynamics that shape the world for generations. We are all, in our own way, path builders. Build with wisdom, foresight, compassion. Don't just innovate. Innovate toward a future that is equitable, sustainable, and just for everyone. The secret pattern behind breakthroughs gives us a map, but we must choose the destination with care.